Thank you, sir. Thank you for having me here.
Yeah. You have about 20 minutes, 15 minutes, okay?
Okay. Can you see my presentation?
Yes.
Yes, perfectly. Thank you.
Yeah, thank you. Um, I'm I'm presenting our team from University of Information Technology to present to you all the binary image classification using convolutional network for V2V communication systems. Um, the main parts of our presentation are introduction, related work, preliminaries of VOCC systems, proposed algorithm, experiment analysis, and conclusion. So public transport systems are invested heavily to serve the travel needs of people. However, the number of vehicles is still increasing significantly each year, leading to overcrowding on infrastructure and a series of problems that need to be solved, such as traffic jams, increasing emissions, greenhouse, and fuel shortage. So one of the possible and effective solution proposed by the research community is the intelligent transportation system. Um, the core the core communication technology of intelligent transportation system are vehicle-to-vehicle communication, vehicle-to-pedestrian, vehicle-to-infrastructures, and vehicle-to-sensor. Um, in V2V communication networks, we see that the vehicles exchange information about their position, speed, and direction of travel, and even road signs. For example, when a vehicle sees an accident ahead, it can send a signal to the vehicle behind to slow down. When receiving this warning signal, the vehicles can respond to agree or disagree with the above warning signals. In V2V communication networks, we see that the
Okay, now you can share.
things. So
Okay, okay.
we last
Thank you.
left stuff right here. I will talk about the benefits of this system. It can support the connection and sharing data between vehicles and people to help limit accidents and unnecessary dangerous situations. It is an effective assistant to assist the network of autonomous vehicles to keep a safe distance. So our project goals are to propose the algorithm for binary image classification for V2V communication system and experimental results of the dataset on the latest state-of-the-art algorithm. We have several questions to answer in this research, which are: how is the performance of deep learning method for V2V communication problem, and analysis of factors affecting the algorithm's ability to classify images. We have some related work for traditional approaches and deep learning approaches before our research. So we're going to learn more about VOCC systems. It all starts with the LED panel installed on the back of a vehicle and a camera installed in the front of the vehicle. The LED panel in the vehicle is to use to transfer signal, visible light signal to other vehicles. Uh, on the road, each LED chip will undertake to transmit a bit. These bits have a value of on or off corresponding to 1 or 0. The collection of bit strings from all LED chips in the LED panel will form a signal used for transmitting and receiving signal. Dashboard camera equipped on other vehicles are used to receive this signal in the form of videos. Besides, it has other advantages, including interference-free compared to radio frequency communication before. And since it can take advantage of the dashboard camera of the vehicle, it has the great compatibility with other computer vision-based techniques such as obstacle, pedestrian, traffic light, road lane detection. So in the near future, these computer vision-based techniques should be installed in every vehicle. This is our proposed algorithm. The proposed algorithm is designed based on the deep learning network architecture. It is used to maximize the accuracy of the bit detection and minimize the bit error rate of the bit classification. It is an end-to-end deep learning model taking on two tasks, which are feature extractor and classifier. So these are the specifications or the parameters of the camera used and the LED panel used. I will go through this because it is many information. So about evaluation metrics, we use BER, which is bit error rate. It is calculated by number of wrong bit LED detection divided by total number of bit LED. We use it along with the attribute LR2A, which is the ratio of LED light to ambient light. About the result, the detector is based on the exception backbone network architecture and using bounding box regression to determine the position and size coordinates of the LED region to remove the background. Then the LED region will be passed through the proposed algorithm to return the result of the binary classification of the LED on or off. The more accurate the location detection of the LED panel is, the more efficiently the sequence of tasks behind it will be handled. OCC does have the limitation in foggy situations, which is currently a heavily researched problem in OCC. So the metric used for evaluating the classification accuracy is BER, which is bit error rate. As we can see in the figure, BER decrease as the ratio of LED light to ambient light increase in range from 0.2 to 1.5. This is because of the increasing contrast between on and off LED as the light ratio increases. However, the BER increases after the light ratio exceeds 1.5. This is because both the contrast and the blooming effect or glare effects increase as the light ratio increases. After the light ratio exceeds 1.5, the negative effect of the increasing blooming effect surpasses the positive effect of increasing contrast and makes that the increasing of the BER. This figure reveals that to achieve the lowest BER, the LED to ambient light ratio should range from 1 to 2. If the ratio is too low, the contrast in the image will be too low too, and the BER will be high. If the ratio is too high, the blooming effect in the image will be too high, and the BER will also be high. So in conclusion, in this paper, in our research, a deep learning-based algorithm is proposed for the bit-led classification task. Specifically, experimental results show that the proposed algorithm achieves an approximate bit error rate metric of less than 12 times 10 to minus second. With BAR metrics less than that, mid-range communication between vehicles will achieve high efficiency. Furthermore, the performance of the VOCC system based on the proposed algorithm is also significantly improved. As a result, communication signals between autonomous vehicles will be transmitted accurately and increase the efficiency of the VOCC system's medium-range communication. That's all our presentation. Thanks for listening.
Thank you very much for your presentation. Now, any question, please? My
What is
question
the
is,
sorry.
okay.
What is the typical distance at which you can still, so this is like probably the percentage depends on the distance, right? 12%. So this is at what distance? Okay, can you show the distance? Sorry.
The distance we used to capture from the camera to the LED panel is about 30 meters to 70 meters.
Okay. And the percentage
so
depends, and the distance, or is the same for the distance? 70 meters probably is more errors than 30 meters, right?
Yeah, it's very far away. So the image will be like not as sharp.
So this 12% is for 30 meters, right?
12%.
No, 12 times 10 to the power minus 2.
Yeah.
It's 12%, right?
We're not comparing the bit error rate in distance here. We compare it in the scale of the ratio of LED light to ambient light.
Okay.
How is your VOCC system depend of the light of day or night and direction between the vehicle?
We do it in both night and day.
Okay.
In the night, it will have more like blooming effect and like glare effect, and it affects the results pretty much. But in the daylight, it is rather more easy to detect.
Mm-hmm. Thank you. Okay, thank you very much.
Yeah, thank you.
The next presentation is the